Hello everyone. So in this video we are going to learn about basics of measure space and what is a measure. This is a very useful concept in measure theory and probability theory, and in future it would help us define what is a probability space and what is a probability, and it will also clear out all of the misconceptions about measure theory and probability theory. Okay, so let's dive into the topic. Let's define what is a measure space. So let's assume that omega is an arbitrary space. So we can say that we have a set called omega which forms an arbitrary space. So let's say we have this set omega which contains three elements a, b and c. You can visually denote it as this, like this. So it has the elements a, b and c present inside, and this is the sample space omega. Okay, so now let's consider a sigma algebra f, which is a sigma algebra on omega. Now in the previous video we had seen what a sigma algebra is. We had defined a sigma algebra. So a sigma algebra is a set of all the subsets of omega such that it is non-empty, the first condition. The second condition is that it should be closed under complement, and the third condition is that it should be closed under countable union, under complement and closed under countable unions, AIs. Okay, so let's make a set like this. So let's see if here for this example we have defined a f as a sigma algebra on omega. Let's see if it matches these conditions. So is it a non-empty set? Yes, it is a non-empty set. It has four sets inside it. So f is non-empty. First condition is satisfied. Is it closed under complement? Let's see. The complement of each of these sets present inside f is also present in f. You can see the complement of phi is omega, which is present in f. The complement of omega is phi, which is also present in f. The complement of set A is BC, it is present in f, and the complement of BC is A, it is also present in f. So it is closed under complement. Now is it closed under countable union? You can manually try that out and you would find that the union of any of these sets is also present in f. Let's say for example union of A with phi is the set A and it is present in f. Similarly you can see that the union of A with BC is omega itself, which is present in f. So it is also closed under countable union. Hence, in this case, f forms a sigma algebra on omega. Okay, so we have formed a sigma as an arbitrary space. We have also formed f, which is a sigma algebra on omega. Now let's define what is a measure. So a measure is denoted by the symbol mu, and you can see that measure is nothing but like a mapping function. So it's like a mapping function from this sample space, as we can see here. It maps from this sample space to the real number line. It maps it to the set of all the real numbers in between closed interval of 0 to infinity. Okay, now let's see what are the constraints on the measure mu. Okay, so let's say we have three elements, and let's take a small example. Let's suppose mu of A is 1, mu of B is 2, and mu of C is 3. Okay, let's define it like this. So this basically means that this mapping function, so this is like a mapping function from any from F, any element, any subset in F to 0 to infinity, the set of all real numbers, the set of all positive real numbers, like this. Okay, so this is the domain and this is the range. So you can see that this set A, we have defined it like this. Okay, but the thing is, you cannot define this and this in this example because B is not a part of the sigma algebra F. So actually this was my mistake, I defined it wrong. So let's cancel these out. So mu can only take in the value any set inside F. Mu can take in any set inside F. Okay, so let's say mu of BC, mu of the set BC, let's say this is 2. Okay, so basically this means that, let's say it has A, B and C. So this is a set, this is another set inside the sigma algebra F. So mu will point from BC to 2. Similarly, mu will point, mu of A would point to 1. Okay, now let's see what are the properties of this. So the thing is that it is defined that mu of the null set should always point to 0. So the empty set, if you take the measure of the empty set, it should be 0, and it makes logical sense because you would use it to measure certain quantities, and measuring emptiness is nothing but 0. So the corresponding point in the real number line, positive real number line, would be 0. So mu, first condition is measure of null set would be 0. The second condition is that, let's say we have some disjoint sets inside the sigma algebra F. So the union of all of these sets, if I take a measure of this would form the summation of the measure of individual disjoint sets. So let's say we have A and we have B and C. These are the two subsets of F, which is a sigma algebra on omega. Okay, so, and we also know that the intersection of these is null set, so these two sets are disjoint. Okay, so now if we want to define mu of A union B C, it should be summation of union, a measure of A plus measure of B and C. So we can see this is omega. So mu of omega is, this is 1 and this is 2. 1 plus 2 equals 3. Okay, so this should satisfy this property always. So these are the two properties, and obviously measure would always spit out a positive quantity, sorry, not a positive quantity but a non-negative quantity. So measure of any such subset in F, AI, is always going to be non-negative. Okay, So let's take one more example. Let's say we have a sample space 1 comma 2 comma, let's say 4 comma 5. Okay, and we define a sigma algebra as this: phi omega 1 and 2 3 2 4 5. So is F a sigma algebra? Yes, it is. As it is non-empty, it is closed under complement. So each of its individual elemental sets have a complement present in F. Okay, so complement of this is this, complement of 2 4 5 is 1, both of them are present in F, so it is closed under complement, and it is also closed under countable union. Take the countable union of any of these sets with each other, it would also be present in F. So F is a sigma algebra on the space omega. Okay, and let's define mu of 1 as 2 and mu of 2 4 5 as 3, and mu of phi is 0 by definition, and let's say mu of omega, what would it be? It would be 2 plus 3, which is 5. So this is an example of a measure space. So we can say that omega, f and mu, which are defined like this, is a measure space. Why is it a measure space? Because f is a sigma algebra on omega. We have already seen this. We have defined a measure mu such that mu of phi is 0. So the first condition is satisfied, and we know that the sum of the disjoint sets on mu is this one. So the union of all of these disjoint sets, we take its measure, it would be equal to the sum of the measure of all of these disjoint sets. Okay, so we have disjoint sets such as this. So mu of 1 union 2 4 5, which would be mu of omega, and this is 5. So the second property is also satisfied, and the third property, that mu of any of the sets present in F. So let's say AI is a set present in F. Mu of any AI is greater than or equal to 0. So if you can see, F is this one. So mu of omega, mu of phi is 0, mu of omega is 5, mu of 1 is 2, mu of 2 4 5 is 3. Okay, you can visually represent this as this. So you have a sample space omega, you have 1 and 2 4 5, you have these elements which are present here, and you can see that the measure mu will map to non-negative part of the number line, which is closed intervals 0 to infinity. Okay, so mu of 1 would be 2, mu of set 1 is 2, mu of this set 2 4 5 is 3, mu of the set 2 4 5 is 3, and mu of 1 2 4 5, that is mu of omega, would be 5. Okay, so you can see this is an example of a measure space. So this forms a measure space. So hence in this case, omega, f and mu forms a measure space. Now I would like to point out one more property of a measure space is that it is monotone in nature. So what is monotone? So monotone is something like this. So let's say I have some arbitrary sample space omega, and I have a sigma algebra F which contains sets A1, A2 till AN and something like this. Yeah. So mu of, let's say we have a set A1 and 8, let's say set of A A3 is present in F such that A3 is the union of disjoint sets A1 and A2. Okay, so the measure of A3 here would be mu of A1 plus measure of A2, since A1 and A2 are disjoint. And let's say we have another set A4 which is a union of 3 disjoint set. Union, let's say A1 2, where all of them are disjoint. A1, A2, A1 2 are disjoint, so they don't have any element in common. So we would always see that mu of A4 is always going to be greater than or equal to mu of A3. Why is that? Because you can expand A4 as mu of A1 plus mu of A2 plus mu of A3, A1 2, sorry, and this will always be greater than mu of A1 plus mu of A2, because the measure of any such AIs is greater than or equal to 0. So this is always greater than or equal to 0, and these quantities are equal. Hence, we can see that this is monotone in nature. That is, the more bigger set is present in the measure mu, the bigger the output it would give. So for in this case, we see that A4 was bigger than A3, so mu of A4 is always greater than or equal to mu of A3. Hence we have seen the monotonic property of this measure. So this is the basics of measure space. So we have learned in this video about how to define a measure space, what is a measure, and in the future videos we will see its uses in measure theory and in probability theory. I hope you liked the video. Thanks for watching.